In this video, we are going to learn how to solve trigonometric equations using fundamental identities. Now, sometimes equations will not have the same trig functions in them, so we might have to use these identities to make them all be the same trig function, or at least factor them in a way to where they all become the same trig function. So we're going to solve each of these equations on the interval of 0 to 2 pi, just so we only use those angles that are on the unit circle. Now this first problem, we have 3 cosine of theta plus 3 is equal to 2 sine squared of theta. So there's a cosine and a sine, which is a problem, because if we go to factor, these will not have any common factors. But if I use the Pythagorean identity, I can maybe switch the sine squared of theta into something that's cosine squared of theta, so that I can factor. And the key here is I just saw something squared, so my mind went immediately Pythagorean identity. So I know that sine squared of theta plus cosine squared of theta is equal to 1. So if I were just to get sine squared theta by itself, it could be rewritten as 1 minus cosine squared theta. So now I could rewrite this expression as 3 cosine of theta plus 3 is equal to 2 times 1 minus cosine squared of theta. Distributing that 2, I have 3 cosine of theta plus 3 is equal to 2 minus 2 cosine squared of theta. And now I'm trying to get a quadratic equation. So if I move everything over to the left side of my equation, I can rewrite this as 2 cosine squared of theta plus 3 cosine of theta plus 1 is equal to 0. And now I have a quadratic equation to factor. Meaning if I rethought of this as 2x squared plus 3x plus 1 equals 0, with x being equal to cosine of theta, I could just factor like a normal quadratic. So two numbers that multiply to positive 2 but add to 3, that would be 2 and 1. So 2x squared plus 2x plus x plus 1 equals 0. 2x times x plus 1, I can factor out a 1. And then my common factor is x plus 1 times 2x plus 1. So this quadratic expression here becomes cosine of theta plus 1 times 2 cosine of theta plus 1 equals 0. Solving both of these for cosine of theta, I'll get cosine of theta equals negative 1, and cosine of theta is equal to negative 1/2. And now I'm just looking for which angles make that true. Cosine of theta is equal to negative 1 at pi, and cosine of theta is equal to negative 1/2 at 2 pi over 3 and 4 pi over 3. You can use that unit circle and just see that that's where the x value is equal to negative 1/2. Now next up, I have tangent squared is equal to 3/2 secant of theta. So again, two different trig functions, but again, I see this trig function squared, so my mind goes immediately to the Pythagorean identity, which is sine squared plus cosine squared theta equal to 1, which initially wouldn't seem helpful since there's no sine or cosine in this expression, but I can create tangent squared by dividing the sine squared by cosine with that quotient identity. So if I were to divide everything by cosine squared of theta, I would get tangent squared of theta plus 1 is equal to secant squared of theta, which there's that secant, so that's great. So I can change tangent squared into secant squared of theta minus 1, and then I'll be set up to replace tangent squared and get an equation with all secants. So I can rewrite this as tangent squared as secant squared theta minus 1 is equal to 3/2 secant. So now every trig function is secant. So now I can possibly factor. But first I'm going to take care of this fraction. I'm going to multiply each side of my equation by 2, just so I don't have to factor with a fraction involved. So multiplying by 2, I get secant squared of theta minus 2 is equal to 3 secants of theta. And then I'll subtract 3 secant of theta. So I have 2 secant squared of theta minus 3 secant of theta minus 2 equals 0. And now I'm set up to factor. So that can be thought of as 2x squared minus 3x minus 2, where x is equal to secant of theta. And again, I'm looking for two numbers that multiply to -4, but then add to -3. That would be -4x and a positive 1x. And when I finish factoring this, I'll have 2x times x minus 2 plus 1 times x minus 2. So I get x minus 2 times 2x plus 1 equals 0. So when I factor this expression, I'll have secant of theta minus 2 times 2 secants of theta plus 1 equals 0. Solving both those, I get secant of theta is equal to 2, and secant of theta is equal to -1/2. Using that reciprocal identity for secant, I know that cosine is its reciprocal. So I can write that as cosine of theta is equal to 1/2, and cosine of theta is equal to -2. Which when solving, cosine of theta is equal to 1/2 whenever the angle is pi over 3 or 5 pi over 3. Now cosine of theta can never equal -2 because the range of cosine is -1. This can never happen, so I will not get a solution from that equation. So my two solutions are pi over 3 and 5 pi over 3. Now on the right, I have cosine of theta is equal to negative sine of negative theta. So these are two different angles, which is already a problem, on top of them being two different functions. So if you ever have a negative theta, we can always use that even-odd property to get rid of the negative. And sine of negative theta is equal to negative sine of theta, because it's an odd function. So when that negative comes out, it cancels out with that negative already out in front. So now I have cosine of theta is equal to sine of theta, which still isn't helpful because now they're not squared and they're two different trig functions. So what could I possibly do? Well, I could use a quotient identity. I have sine and cosine, and tangent of theta is equal to sine of theta over cosine of theta. So if I divide each side of my equation by cosine of theta, I'll get 1 is equal to tangent of theta. So now my problem comes down to when is tangent of theta equal to 1, which now is a single trig function, and I don't even need to factor. So I'll have here, which angles make tangent of theta equal to 1? Well, that happens at pi over 4 and 5 pi over 4 on my unit circle. And lastly, we have secant of theta equals tangent of theta plus cotangent of theta, which is three different trig functions. But there is a way to possibly get down to at least 2, and then we can work from there. So we have plenty of reciprocal and quotient identities that we can use. So you make everything just sine and cosine, which we learned earlier we can sometimes combine into one trig function. So we know that secant of theta can be rewritten as 1 over cosine of theta, because they are reciprocals. Tangent of theta we just went over as sine of theta over cosine of theta. And the other quotient identity would be cotangent of theta is equal to cosine of theta over sine of theta. So now I'll replace all of these with those expressions. Now I'm down to just sine and cosine, which is one less than 3 different ones. So I'll have 1 over cosine of theta is equal to sine of theta over cosine of theta plus cosine of theta over sine of theta. Now I have two different functions, but first, just like I got rid of that denominator of 2 over here, I can do the same thing with trig functions. I can multiply each side of my equation by cosine to get rid of these cosine denominators. So if I multiply each side of my equation by cosine, which I'll indicate just by doing this. So cosine of theta on both sides. The cosines will cancel. I'll be left with 1 is equal to now sine of theta. But that didn't cancel out with the sine denominator over here. So I'm left with cosine squared of theta over sine of theta still. But in order to get rid of this denominator, I can multiply each side of my equation by sine of theta, so it can cancel out with that denominator. So now I'm left with sine of theta is now equal to sine squared of theta plus cosine squared of theta. And that's still two different trig functions with sine and cosine, but I have some trig function squared, which is the Pythagorean identity. Sine squared plus cosine squared of theta is equal to 1, so this equation simplifies to theta is equal to 1. And now I'm like, what angle makes sine of theta equal to 1? Pi over 2, the uppermost point on your unit circle. And that is how you solve trigonometric equations using fundamental identities.